So, good afternoon. Today we are going to talk about synchronization. From my point of view, this is I would say, so from technical point of view, this is the one of the two most important things to remember from this course. So the one thing is like how to work efficiently with memory. And the second thing is how to efficiently synchronize multiple threads, because both these techniques or these parts of the technology stack can make your program significantly slower. I guess that most of you, or that's my experience from other students, they somehow understand that memory can be slow, and working efficiently with caches and memory and so on makes your program faster. But my experience is that understanding synchronization is much more difficult, and students at the exam often do not understand it well. So that's why this lecture is here. That's why I think this lecture is important, because as you will see, you can significantly slow down your program if you do not synchronize your threads efficiently. And today we will talk about why is that so complex, which options we have, and how to do synchronization efficiently, at least in some cases where it's possible to do it efficiently. So synchronization, just to be sure what I have in mind. We all know that all our computers today are multi-core. We will have more and more core in the future. So if we want to use all this computational power which is provided by these multi and many core CPUs, we have to write parallel programs. If we write parallel programs, in order for this parallelism to be useful, those threads or parts of the program which run in parallel have to communicate. Otherwise, it's like running certain number of independent programs. So there must be a communication. And this communication, that's what we call synchronization in this lecture, because every communication is some kind of synchronization. If I'm sending data, it means that on the other end, somebody waits for this data, so they synchronize their execution. Somebody is sending data, the other is waiting on the data, and the execution is synchronized. So I will talk about synchronization today, but it's not anything magic. Whenever you communicate between different threads, this is some kind of synchronization. And it can be a big source of performance problems. I have already said that. So you probably also know like some basic forms of synchronization. Perhaps the most well-known and the most used form is like mutual exclusion, which basically means that you use a mutex to protect some shared data structure. Whenever you want to access that shared data structure, you just lock the mutex, access to the data structure, and then unlock the mutex. And the mutual exclusion property means that there is just one thread in your program which can access the data structure at a time. So it's exclusive access. If I am accessing the data, you cannot access, you have to wait. When I am done with that, somebody of you can access the data. But this is just one example. There are many other forms of synchronization. Another common example is producer-consumer synchronization, where I am producing some data and you are waiting for them. That's typically the case if you have some like web application, you are sending requests to database, so the database is consumer, you are a producer of the request, and with the response from the database is the opposite. The database produces the responses and you are waiting for the response. So this is also a kind of synchronization between different parts of the program. So it's very common. And if you don't handle this synchronization properly, things can go wrong. To demonstrate what what all can go wrong. I have this simple example here. So this is, if I ask like students in the first year of bachelor how to synchronize multiple threads, this is like what they typically come up with. So who can tell me what's wrong here? At least one thing. Yeah, busy waiting is one thing. Another thing. Yeah, there is really a lot of problems. So another problem is that here we check for some condition and then modify the condition variable, and this check and modification is not atomic. So it can happen if there are multiple threads running this function. It can happen that two threads at the same time check that this condition is false. They exit this busy waiting loop, and then both threads will enter what we call critical section, which is like this modification of shared data, which should be protected by this lock. In this case, we want to implement something like mutex, but actually without the mutex, with just simple Boolean variable, and this non-atomicity between this comparison and this modification, this is another problem. We will see that there are many other problems, like that the compilers can optimize memory accesses. Compilers can reorder access to variables. Not only compilers can do this reordering, you already know that hardware also reorders memory accesses, which also causes problems with synchronization. If you do this kind of synchronization, you can easily deadlock your program, and by busy waiting you waste the energy. So we will look at these problems on subsequent slides, and I will show you how those problems are solved, so that if you can't, for whatever reason, use just plain mutex, you can at least know how which technique to use to avoid these problems. But before we start with that, I would like to quote one clever guy, Paul McKenney. Paul McKenney is a developer of the Linux kernel. He is the brain behind what's called RCU. We will talk about RCU at the end of the lecture, and RCU is the technology which allows the Linux kernel to run efficiently even on supercomputers. So if you have supercomputer with like 4,000 or 8,000 CPUs, without RCU, it would be impossible for the Linux kernel to run on such supercomputers. And this guy, who is responsible for this technology, says that implementing correct synchronization primitive is like committing the perfect crime. There are at least 50 things that can go wrong, and if you are a highly experienced genius, like he probably is, you might be able to anticipate and handle 25 of them. Yeah, so that's said by this guy. Now, here I mentioned just 6 of those problems, so there is 19 more that I didn't mention here, and mortal person is able to fix them, and then there is 25 more which even like mortal person is not able to handle things correctly. So synchronization is tricky. If you can, don't try to invent your own synchronization primitive, synchronization mechanisms. Use whatever is available. If whatever is available doesn't work for you, or it is slow, inefficient, then you have pretty difficult task in front of you to solve. So that's synchronization. Now let's look more briefly or in more details why is actually the synchronization complex. And the problem is that synchronization is related to working with shared memory. You have data structures in your memory. This data structure, for example, one structure in memory is shared between multiple CPUs. In this lecture, I will somehow interchange the terms like CPU and thread. I will somehow assume that there is one program thread running on each CPU in the system. Of course, it can be differently, but for this lecture, assume one thread equals one CPU. So here, different CPUs, different threads access some shared data in memory, and they have to synchronize with accessing to that memory, because if they, for example, write to those data simultaneously, there can be some inconsistency in this data structure, so they have to synchronize. And the problem is that it's not like that this CPU or that CPU directly works with data in memory. There are a lot of caches, so there are multiple level caches. Here we have just two levels, like level 1 cache, level 2 cache. You know that there is even level 3 cache. And also typically CPUs implement something which is called store buffer, which is kind of intermediate memory used for when you write data to memory. This intermediate memory somehow holds the queue of the writes, because waiting for this slow memory would stop the CPU from execution, so the pending writes are somehow queued here and then they are stored to the hardware later. So the problems. So one problem is this store buffer, for example, that writing to memory doesn't mean that this memory is immediately modified. The modification stays in the store buffer. Not only in the store buffer, but the modifications can also stay in cache memory, either here or here. Which means that whenever another CPU wants to access the same data which were modified, let's say by CPU 0, there has to be some kind of communication between the CPUs. And as you know, speed of light is limited, so this communication between the CPUs is slow. And if the CPUs have to communicate with each other, asking like, hey, do you have newer data which I want to access, this is just slow. So the CPU is the fastest if all the data is located in its local cache memory. There is no communication with other CPUs in the system and so on. Once you have to communicate with other CPUs, and by this communication we are just meaning like reading or writing memory, because reading and writing memory here is just a communication in this system by using this interconnection bus and so on. So yeah. You can basically see a multi-core CPU as a distributed system, and memory is another node in this distributed system, and all memory operations are basically communication, sending and receiving messages in a distributed system. And this causes the problem, this makes operations slow and so on. If you studied distributed systems in some other course, you have probably heard about some theories about event ordering in distributed systems, and that sometimes it's quite difficult to figure out which event happens before the other and so on. So the same situation is in such a computer system, multi-core system with shared memory. And the key thing to realize is that operations with memory do not always synchronize with each other. What I mean by that? So imagine you have a thread of execution, and there are multiple instructions executed by the thread. If this is just one thread, things are simple, because the order of instructions in the program gives the order of events, and it's clear what happened before the other event. You know that CPUs do not execute the instructions in the same order as they are given in the program, but what CPUs guarantee that the outcome of the execution will be the same as if the executions were executed exactly in that order. So from that point of view, we say that events in a single thread have total ordering, which means you always know which event was first and which was second, and so on. For the purpose of talking and reasoning about synchronization, people define relation which is called happens before relation. And the key property of this happens before relation is that it's so-called partial ordering. Partial ordering means that if there are two events, let's say P and Q, you cannot say which event happened first and which was the second, because it's simply not defined. And this undefined, let's call it undefined behavior, simply allows the computer hardware to be efficient. So it allows the computer hardware to be efficient, but it can cause some headaches to software developers, programmers, because it's like not very nice property. So whenever you are writing multi-threaded programs, you always want to, if you communicate from one thread to another thread, what you need to ensure that there is always happens before relation between the events leading to some read or modify data. So here, all instructions in a single thread, there is happens before relation between those instructions, but there are only certain operations typically implemented by mutex which ensure that there is happens before relation between multiple threads. Yeah, so this is very simple example showing that if you unlock a mutex, it creates happens before relation between this unlock operation and another lock operation in another thread. And there is also happens before relation between modification of data and this unlock operation. So if you read this data in another thread, for your program to be correct, to behave correctly and deterministically, there must be like pass from this graph of happens before relation from this data modification here and data modification here. If, for example, there is not a mutex, you just forget to use the mutex here, there is no pass from this graph, and this means that you have race conditions in your program. Sometimes your program will behave correctly, sometimes it will behave incorrectly, randomly, sometimes it will crash, and so on. So those who program in C or C++ probably know this very well. Sometimes the programs behave strangely, and that's one of the reasons that you just forget to properly synchronize. This is this synchronization that we will talk about, which manifests or which implements this happen before relation, which is used in theoretical reasoning about that. So this is the connection to like theory of distributed systems, and now let's look at the problems that we have identified at the beginning, and let's look at how these problems can be solved. I have said that the first problem is non-atomic data manipulation. So what I mean by that? Imagine that you have a simple, let's say, integer variable called data, and I want to increment this variable in multiple threads. If you are lucky and have a good compiler and whatever, this C operation, this C expression will be translated to a single machine instruction, at least on x86 platform. This machine instruction will be something like increment and data. This will be the address of the increment. And if you remember well computer architectures course, you probably know that single instruction is atomic. But the single instruction is atomic with respect to the interrupts of the CPU interrupts, the instruction cannot be interrupted by interrupt. But even a single instruction is not atomic with respect to memory accesses. Why? Because such an instruction is implemented in hardware that this memory bus is used to read data from memory. Then the increment is calculated with arithmetical logical unit, and then memory bus is used to write the data back to the memory. And of course, if you execute this same data increment operation in another thread, it can happen that the operations interleave like this. Both threads basically reads the same data from memory, they read 0. Both threads just increment that value to 1, and then both write 1. And perhaps your goal was, if you have 2 threads incrementing a variable, the result should be 2, but here the result is just 1. And the reason is that this instruction, even though it is single instruction, the operation is not atomic with respect to memory accesses and this low-level operation on hardware buses. So if you want to ensure that this does not happen and just incrementing this data variable twice results in the value 2, you have to execute, or you have to force the CPU somehow to execute this instruction atomically. All modern CPUs, especially those which have multiple cores, implement in hardware atomic operations. Either those atomic operations are special instructions, or in case of x86, this is like a special prefix to an instruction. Different hardware architectures implement this differently. So for simplicity, I will talk here about typical atomic operation, which is called compare and swap. And this is typically, or it is proven that if a CPU implements just this single atomic operation, that they atomically compare some variable with another value, and if the comparison is true, the value is swapped with another value. And it is proven that if you have just this single instruction, you can implement all other atomic operations that you need with this single instruction. So this is a typical example. x86 architecture implements this instruction with CMP exchange, or this operation with CMP exchange instruction. And so you can, if you want to use this, you can either use inline assembler in C, or if you don't like inline assembler, or if you want your program to be portable to different architectures, you can use, for example, in C, not C++, in C, in GCC there is an extension which is called, and I think it's no longer in GCC, it's also in other compilers, __ atomics exchange _n. You specify the pointer, the value for comparison, and some value which I will talk about later. And this will basically force the compiler to generate this atomic compare and exchange, or compare and swap instruction. So going back to our initial example, I said that this comparison and setting of the value is not atomic. So if we have this atomic exchange function, which the compiler translates to an atomic instruction, we can re-implement this condition and setting of logs true in this way, and we get rid of the problems with atomicity. Now, if we have code like this, it's always guaranteed that there will be only one CPU which succeeds this condition, and the other CPU will just busy wait in this loop here. This is atomic instructions and how to use atomic instructions from C. So if you are interested in other atomic instructions, since C11 and C++11, which are the standards of the C and C++ language, and 11 stands for like 2011 version of the standard. C defines that there is a header called std atomic, which defines those atomic instructions. So you don't have to use this underscore, but you can use directly atomic something. And similarly, in C++11, they introduced a header file called just atomic. And this atomic header file defines a template variable. So if you need atomic integer, you can use this C++ template parameterized with integer, and this is how you define integer variable x. And whenever you access this variable, the all operations on this variable are guaranteed to be atomic. So for example, you can write x++, and this will translate into atomic increment operation. So very easy. The question now is, okay, so I will use all my variables will be atomic and I will have no problems. You will have no problems with correctness of your program, but you will have problems with performance of your program, because as we will see later, those atomic operations are typically many times slower than non-atomic operations. So it's good to not use them everywhere, to not waste with them. So the question is, why they are slower? And we have already seen this picture. If you want to do, let's say, atomic increment, basically you are saying, I want to increment the value which is somewhere here. But the problem might be that this value is not only here. Maybe other CPUs have this value in the caches. So before one CPU can do this atomic increment, it has to, in the worst case, communicate with the other CPUs, asking, hey, CPU1, do you have my variable x in your cache? If yes, please throw it away so that I can modify it. And then, please, CPU number 2, do you have this variable? Yes, please throw it away from your cache, I will modify it, and so on. So this is like broadcast operation. You have to contact all the other CPUs and ask them whether they have, or not the CPUs, just the caches here, but it's the same, and ask them whether there is a copy of this data, and throw it away. You have probably heard about cache coherency protocols, which is a protocol which is used on this bus here, and the computer caches of different CPUs communicate by using this protocol with each other. And this protocol is used to optimize this communication. So it's not always necessary to like do this broadcast, because due to this protocol, the CPU may already know that other CPUs do not have this data in the cache. So you have probably heard about this messy or massive protocol, where the letter E stands for exclusive access. So if the CPU know that it has this data in its cache with exclusively, meaning that no other CPU has data in their cache, the CPU can directly execute this atomic instruction in its cache. But if the same data is not exclusive in the cache of just one CPU, maybe it's shared between multiple caches, or it's not present in this cache at all. There is this communication, broadcasting, and so on, and things get slower. So to demonstrate how slow it is, or how much slower this atomic instruction can be, here you can see some benchmarks on some quite old, but the numbers are not very different today system. There is this compare and swap instruction, and how long does it take to execute this instruction under different circumstances. So if everything is all right, the fastest operation in this case was 19 clock cycles. If things go wrong, and there is not only this atomic instruction overhead, but also cache memory overhead, there are cache misses. The worst case execution time is 266 and something times slower than a single clock. So you can clearly see if all instructions are atomic, your program will be just 20 times slower, and only if you are happy. It can be even slower if you are not that happy. That being said, those are atomic instructions. So at the rest of this lecture, you will see that if possible, we want to avoid these atomic instructions because they are inefficient, but we cannot avoid them at all because we would have just a single-threaded program if we don't use them. Besides atomic operations, we will also talk about operations which are called barriers. And you will see that barriers are more efficient, and the reason why barriers are more efficient is that they do not communicate with other CPUs. Barrier is an operation which is only local to the CPU which executes it, and that's why it is more efficient, and it can be also used for some kind of synchronization. So we will see later. So this was related to atomic instructions. Another problem that we have identified in our simple program at the beginning was compiler optimizations. So let's look at this simple program. This is just part of what we have seen there. And if you look at this program from the perspective of optimizing compiler, you can see that here we are reading the locked variable, and then we are modifying that variable and modifying it again without actually reading. So what good optimizing compiler will do, it sees that this is like dead store. The data stored by this statement is never used by this program here. So the optimizing compiler will just remove this line from the program because it seems useless. The compiler doesn't know that this data might be important for other threads because the compiler assumes, unless there are atomic instructions, the compiler assumes just a single thread of execution. So this seems like completely useless instruction, and the compiler can remove it from the code. Similarly, you know that the compiler tries to reorder instructions. So for example, it can, for whatever reason, it can reorder, it can put this data behind this locked equals false because it thinks it's clever thing, it will run faster, for example. Because just from this program, the compiler doesn't know like that this operation is somehow related to this data. It doesn't use the same variable, so the compiler doesn't know that this is somehow related. If you have a situation like this, you may, I have already talked about that, you know about the volatile keyword. So if you know your compiler is optimizing something that you don't want to optimize, you can use volatile keyword. And similarly, to prevent this reordering, not only like removing this line, but to prevent reordering, we can also have compiler barriers. Talking about the barriers, we will talk about two kinds of barriers. So this is compiler barrier, and later we will talk about hardware barriers. The principle is the same, but one is for the compiler, another is for hardware. So with all those things together, we can change our code like this. We define this variable as volatile, which will tell the compiler whenever I am reading or modifying the variable, just do what I write in the program, read or write the variable and do not do any tricks there. And if you want to ensure that this logged access and data access is not swapped, you have to put the barrier. In this case, this is a compiler barrier. In case of GCC, this compiler barrier is implemented as a volatile assembly statement with no instruction, but this memory ordering specification. So this is just some kind of trick how to implement this barrier. And the barrier means just it prevents the compiler from moving memory operations before that barrier, after that barrier, and vice versa. So whatever is before barrier stays before the barrier, whatever is below the barrier, which is in this case just this operation, stays after that barrier. So this way you can prevent this problem, you can prevent the compiler from incorrectly optimizing your memory accesses, and it will somehow behave correctly. Don't do that, because all volatile memory accesses or all of that will become just slow. In many cases, you don't need all memory accesses to this locked variable to be volatile. We will use that later in the lecture, where we will use macros named like access once, load shared, or store shared. And as you can see, those macros are implemented that you have some variable x, you create a pointer to that variable, you typecast the pointer to the same pointer but to volatile variable, and then you dereference the pointer. So this is a tricky way how you can make just a single access to a certain variable volatile, and how you can prevent the compiler from optimizing just that single access and not the others. And then if you want your program to be readable, you can annotate it or create an alias to this access once macro for loading and storing, so that it's clear like which operation you have in mind. So that's about compiler optimizations, volatile accesses, and compiler barriers. Now let's look at the same thing but at the hardware level. Hardware also optimizes the execution on the instructions. And if you look at, this is a table from Wikipedia which compares different computer architectures, and different computer architectures differ not only in the instructions implemented but also in memory consistency models they implement. And typically memory consistency model is defined by defining, for example, here this line corresponds to if there is one load instruction followed by another load instruction, whether the hardware is allowed to execute those instructions in different order. So as you can see, many computer architectures allow reordering loads after another loads. And then other lines of the table, loads reordered with stores after them, or stores reordered with stores after them, and so on and so on. As you can see, many computer architectures allow this kind of reordering. One peculiar architecture which doesn't you cannot buy it anyway today because it's no longer exists, but it's called alpha, but it's all red. Alpha allows reordering everything with everything. On the other side of the spectrum is AMD 64. There is just one red line here. The everything else is green. What does that mean? If you are using your software only on x86 architecture, it might be that problems in synchronization, you will not see them, because somehow the architecture guarantees a lot of memory ordering in operations, and the hardware is not allowed to aggressively reorder those accesses. But if you, for example, then port your application to a mobile phone, which is running on ARM, and we can see ARM, this is some older ARM, but for newer ARM, the table is similar. You can see that ARM is almost like alpha. It can reorder everything with everything else, only certain load ordering is guaranteed to stay the same. And then your application will stop working there if you don't have your memory ordering correct. So that's a bit tricky, because it seems like you have your program correct, but then you run it somewhere else and it's not correct. So have that in mind. By the way, this is one of the reasons why ARM CPUs are more memory efficient than CPUs, because the hardware doesn't need to track this memory ordering and instruction reordering and these things. The hardware is much simpler due to that it is able to, or it is allowed to do this reordering, and therefore, because the hardware is simpler, it is less or it needs less power to execute. On the other hand, the programmers need to pay attention to synchronization more than in case of x86 here or here. Yeah, so what we need to do to prevent reordering at hardware level, the answer is the same as before: barriers. Here it's not the barrier, the compiler barrier, but it's a barrier instruction. And for example, on x86, those barrier instructions are called fans, like memory fans, M fans, it's so-called full barrier, or L fans, which is like load fans, prevents reordering between loads, certain loads. On different architectures, the instruction names are different. So, for example, on ARM there is DMB instruction, which stands, I guess, data memory barrier instruction, and the purpose of this operation is the same as in case of compiler. So it prevents memory operations that are stored in the program before this barrier instruction to be executed after this barrier instruction. So barrier actually acts as a barrier, and nothing on top of it can go behind, and vice versa. Later, when we will talk about RCU implementations, you will see a function, C functions, which will be called CMP-MB, symmetric multiprocessing memory barrier, and this is hardware independent implementation of that memory barrier instruction. So on x86 this would be implemented with mfans, on ARM this would be implemented with DMB instruction. Yeah, so those are barrier instructions, but typically people don't want to deal with inline assembler unless necessary, because yeah, it's too tricky. So the good thing is that you don't have to, since C++11 all of this is somehow provided to you at C++ level by this C++11 standard. This standard defines atomic load and atomic store methods. And those methods, and not only those but all the others, have a parameter which is called order. And this order defines requirements for memory ordering when the CPU executes this instruction. Don't be confused by that it's often also used with atomic instructions, because the ordering is not defined for these atomic operations. If it is just an atomic operation, the atomicity is independent of ordering. So atomicity is one thing, and the ordering is another thing. And the ordering, we are always talking about ordering between this atomic operation and all the other reads and writes in the same thread. So if you look at the documentation, what can be the value of ordering, you can see that one value is relaxed. It means there is no ordering requirement. So if you execute an atomic instruction with relaxed ordering, this means that this will be just atomic instructions and no ordering. And then if there are some other options, the most strict option is sequential consistency, which is this one at the end, which means that everything that happened before that memory instruction will be ordered before that instruction, and everything which happens after it is ordered after it. And this is just how you specify it in the source code. Typically what the compiler does and how the compiler implements those ordering parameters is that the compiler inserts those fence or memory barrier instructions into the generated code. So depending on what you specify here, the compiler puts the barrier before, after, or before and after that operation. So to demonstrate that on an example and to go back to this happens before a relation, imagine that we have two variables. We have a normal variable which is called data, and we have an atomic integer variable which is called owner, and this owner variable will define who can access this data. So this will be kind of lock specifying which thread is allowed to access the data. And so let's say we owner is initially set to 1, so we can access the data, we can modify the data variable. Then we use the store method on this atomic variable, setting this owner to number 2 and specifying memory order release. And if you read this documentation, what does release means? It just means that whatever reads or writes were before this store operation, those reads or writes will be visible on another thread yeah, and now I see there is there is a mistake in this slide. So this read should be here. So I'm sorry, just move this read to the right. If the other thread does a load operation and specifies the memory order acquire, it just means that whatever happens after this acquire will actually happen after this load operation. And together, these operations with release and acquire semantics, they implement this happens before relation. So that's why I put the arrow here. And this is how you can, if you don't want to use mutexes, how you can implement and properly synchronize threads in C++ between different CPUs through this ordering. If you use mutexes, you can forget about this because mutexes have all of this inside. So you just use mutex lock, mutex unlock, and mutex lock basically is acquire operation, mutex unlock is release operation, and this just works. We can continue talking about the problems and solutions. I will just go quickly over that because it's not that important. You can read it in the slides. So another problem with this homegrown synchronization is that it can easily lead to deadlocks. To prevent the deadlocks, you can't implement mutexes just in user space. You have to somehow coordinate the implementation between the application and the kernel. We will talk more about that later. And another problem is busy waiting. So you already know that busy waiting is problematic. You consume energy and so on. So by using proper mutexes which coordinate synchronization with the kernel and blocking the kernel and so on, you avoid this busy waiting. However, it's not always possible to avoid busy waiting if you are implementing the operating system. For example, there are places where you cannot simply sleep, and in that cases, busy waiting is just necessary, and it's so necessary that it even has a name, and this name is spin lock. But this is typically you never need a spin lock in an application. You just need them inside operating system or in some very special cases. So that's the background, that's the problems that we can get and how we can solve those simple problems. And now let's look at nobody wants to implement what I have just talked about. Nobody wants to implement it from scratch. We just want to use it. Somebody has already implemented. So what we can use? Of course, we can use mutexes. Every programming language or most of the programming languages offer something like a mutex, at least C, C++, Java, and many others. The thing is that using mutexes is very simple. There are just two operations, lock and unlock. If you lock, you run critical section. At the end of the critical section, you unlock, and other threads can continue. There are many ways how mutexes can be implemented. For example, due to the requirement that it needs to coordinate with thread blocking, they can be implemented inside the operating system kernel. But as you will see, performing system call for every lock unlock operation could be very expensive. So there are some ways how mutexes can be implemented more efficiently. In case of Linux, this is called Vutex, and we will talk about that shortly. What I want you to remember and to always bear in mind, whenever you use mutex, there is always atomic instruction. So locking and unlocking in every mutex is implemented with atomic instructions. And as you have seen, atomic instructions have some overhead. So just using locking, unlocking has some overhead. So if you want to have efficient, scalable programs, you just want to reuse locking, unlocking as much as you can. But yeah, there is a trade-off. You will see. So it's not like it's not easy. There are trade-offs that you have to make. Yeah. So kernel semaphores. Kernel semaphores. I have just said it. The semaphore which decides whether you are allowed to enter the critical section or whether your thread gets blocked waiting for another thread is implemented inside the operating system kernel. And the problem is that the system call overhead on today's system is something like 100 clock cycles. So if mutexes are implemented purely in the operating system kernel, they would be very expensive operation. For that reason, Linux and other operating systems implement something which allows to reduce this overhead. In Linux, it's called Vutex, and Vutex is a shortcut for fast user space mutex. And the idea is very, very simple. If the mutex is uncontended, meaning that the mutex is unlocked, and you just log the operation, execute short critical section, and unlock it, and there is no other thread waiting for that mutex. All the lock unlock operations are implemented purely in user space with just an atomic instruction. So Vutex, remember, even semaphore is just a counter and a queue. And if that counter is implemented with atomic variable, it can be atomically incremented and decremented purely in user space without any system call overhead. So you have seen that this atomic instruction in the best case takes like 19 clock cycles. So it's much better than 100 clock cycles. So it's more efficient. On the other hand, if you want to lock the mutex, you execute the atomic instructions in the user space. And then you see the mutex was already locked, so the atomic instruction compare and SWOT, for example, fails. then you have to wait for the owner of the mutex to release it. And in that case, there is a system call which is called futex wait. The program simply calls to the operating system kernel saying, please block this thread and wake me whenever this futex is unlocked. The current owner of the futex, whenever it unlocks the mutex, it sees, there is somebody waiting for that mutex. So instead of simply incrementing that atomic variable, it calls to the kernel, calls something like futex wake, and waking one or more threads waiting for the futex. So the idea is pretty simple, and you all are using futexes all the time, because futexes are the underlying implementation for most of the synchronization primitives in Linux. So mutexes are implemented using futexes, semaphores are implemented using futexes, conditional variables are implemented with that, thread barriers, read-write lock, basically everything has mutex under the hood, has futex under the hood. So futex is just an implementation of those higher level synchronization primitives. In the second part of the lectures, when you will talk about Java virtual machine, you will learn that Java implements something which is called syn/fat locking, and the principle is basically the same. This is used in Java to implement the synchronized keyword, and every object in Java has the mark word in its header, and this thin locking is basically like atomic instruction on that mark word, and only if multiple threads want to lock or synchronize with the object, it calls the operating system and actually blocks. Otherwise, this is just atomic operation. So what I want to say, that Linux calls that futex, Java calls that thin fat locking, but the principle is the same. And I believe if you read the literature of other operating systems, they use the same mechanism but call it very differently. So be aware of that. And yeah. So what's important is to understand how the thing works, know how it is called, because typically same mechanism is called by multiple names. Yeah, so these are futexes. Those are more efficient than kernel semaphores, but they are also tricky. One of the reasons why futexes are tricky, and if you want to implement something like futexes on your own, if you want your software to be reliable, you would have to implement those tricky parts. And what's tricky is that, for example, it's possible to share a single futex between multiple processes. So you can have just shared memory between multiple processes. For example, if you do fork or whatever, if you just explicitly share the memory, there can be futexes. And the problem is if one process locks the futex without calling into the kernel, because that's the key principle, and then the process crashes. If the process crashes, then the futex remains locked forever, because the one who should be responsible for unlocking it has already crashed, cannot unlock it. So it would lead to the deadlock. So if you study how it is implemented in Linux, you would find something which is called a robust futex. There is more operations around that, and basically it allows that even if the process crashes in the critical section inside the futex, the Linux kernel recognizes that and unlocks the mutex on behalf of the crashed program, so the system doesn't deadlock and the system is robust. Yeah, so this is like efficient locking, and now let's look more into detail what is actually cost of locking, cost of mutexes. Imagine we have a multi-socket CPU. So this is like this is a single quad-core CPU, and we have a motherboard with 4 quad-core CPUs. So it's nowadays we have much more CPUs, but we still can have motherboard with 4 sockets. Nowadays, each socket would have, I don't know, like 32, 64 CPUs. The situation would be similar. So what are the limiting factors limiting the performance of such a system? You already know that one of the limiting factors is speed of flight. If you imagine how distant would those CPUs, those sockets be on the motherboard, it would be like at least 10 centimeters, one from each other, and you know that speed of flight can barely go this 10 centimeters in one clock cycle in vacuum, and electricity doesn't go in vacuum, so just the fact that the information has to go from one socket to another is a limiting factor. And you know there are more factors like the gates and communication protocols and so on. So now imagine that all the CPUs running here just want to execute atomic increment instruction. There is a single data variable, and all the CPUs want to atomically increment this variable. By the way, this is a typical case if you have some statistics. So you have some, I don't know, network router or whatever, and you just want to know how many packets there went through the router. So whenever one CPU routes a packet, it increments this statistics counter, like I have routed 1 packet. And if all CPUs do just that, this is actually what happens. So whenever let's say the CPU, or let's start here, whenever the CPU wants to execute this atomic increment, it first needs to ensure that the data to be incremented is exclusive in its cache. So it loads the data from the cache, can increment and stores the data in local cache. Now, another CPUs also want to increment the same data, so there is this cache coherency protocol which those CPUs all communicate. So the cache line with modified data goes from one CPU to another. Now the CPU can increment it, and so on and so on and so on and so on. So the data just flows through caches of all the CPUs in a cyclic manner, leading basically to execution. Only one CPU is executing, the other CPUs are just waiting for memory, or in this case for interprocessor communication to deliver the data that the CPU works with. As you can imagine, it doesn't help to have 16 CPUs in this case, because all CPUs are just waiting and not doing anything useful. If you want to have your program running efficiently, you somehow have to structure the program that it works in this way, that all CPUs just work with local data and synchronizes by memory reads or writes with all the other CPUs as little as possible, so that you can use the computational power of all the CPUs. So I hope that's clear. Now let's look at the overhead of locking. So you already know that each lock somehow involves atomic operations. This atomic operations is involved in both lock and unlock operations. So typically what you do with a mutex, you lock the mutex, perform the critical section, and unlock the mutex. So now imagine that the critical section is just an increment of a single variable. So you want to lock a mutex, do this increment, and then unlock the mutex. You already know that if there is some cache miss, for example, because the lock is can behave exactly like this. So the lock is just a variable, the mutex is just a variable, and if all threads are locking and unlocking the mutex, the memory travels through all the system here and there, and all threads are just waiting for the lock. So if this is the case, the initial locking just takes long time because the memory storing the log has to come to our local CPU from another CPU which has logged that log before. Once the cache line arrives, the compare and swap instruction, or how is the log implemented, can finish. We can execute this critical section which is in green here, which could be like 1 clock cycle. And then, if we are lucky, we can unlock the critical the lock again in one clock cycle. And we are lucky only if the memory where the lock is stored stays in our cache. So there was nobody who would just stole this memory from us. Then the unlock operation would be fast. However, if the system is heavily contended, meaning that there are many threads, all threads are trying to lock the memory, it can happen that while we are executing this single instruction, another CPU tries to lock our lock. And because it tries to lock it, it means that the hardware does just this. It sends the data with the log from our cache to the cache of another CPU, which means that after we execute this single instruction, we again have to wait for the log to come back to our CPU so that we can unlock it. So as you can see, mutexes and locking has pretty high overhead, and the overhead is the higher, the more contended the lock is. So if the lock is uncontended, the overhead is pretty okay, but the more CPUs you have and they want to lock the lock, you pay the overhead basically twice, once for locking and once for unlocking. So that's another reason why you want to avoid locking, why you want to avoid atomic instructions. And if you in another lecture you will, or in the rest of the lecture, we will see how we can avoid this locking at all for certain kinds of workload. For another lecture you will see how you can avoid locking with lockless algorithms. The advantage of lockless algorithms is that per operation there is typically just one atomic instructions, so you pay just this overhead once, and you cannot pay it twice as you pay it if you use locking. So you will see about this lockless and non-blocking algorithms later. Now we will look at a special kind of workload which is quite often nowadays and which allows to highly optimize the synchronization behavior. And this workload is called read mostly workload. So imagine you have some shared data. Most of the threads just read the data, and from time to time there is one updater which just updates the data. So this is called read mostly workload because most of the time you have some readers, and from time to time you want to update the data. So if you have this read mostly workload, and you want to use mutex to synchronize access to the data, this is the result. So if there is just one reader, it's okay. But if there are multiple readers, for example here, this reader wants to start reading, but it cannot because there is another reader which is just reading. Then there is updater, and basically at any time there is just one CPU which can execute something useful. So that's clearly the problem of mutex. Mutex means mutual exclusion, but we don't want to have mutual exclusion for read mostly workload. For read mostly workload we would like to read as much as we can, and only maybe wait if we are updating the data. Just some examples of read mostly workload. All kind of caching basically involves read mostly workload. So if you are developing a website where you cache like pre-rendered pages, or if you are some cloud provider providing content delivery network, this is all about read mostly workload. The whole internet is just reading. Only from time to time somebody updates some data, file system, DNS, distributed data. These are all examples of read mostly workloads. Thousands and thousands or millions of clients are just reading the data. Only from time to time somebody updates the data. Yeah, so clearly using mutexes for this kind of workload is pointless. Most likely you have heard about read-write logs, which allows to implement synchronization for readers and writers separately. And with that, read-write log allows that multiple readers execute concurrently, and only if you are updating data, no reader can execute. So this read-write log, it's much better than using mutexes, of course. But the problem of read-write log is that as a mutex, both read-write logs, they use atomic instructions in log and unlog operations. And as you know, atomic instructions can be slow, they scale badly, and so on. So this picture is much better than what we have seen before, but there is still too much of red color here. Ideally, we would like to get rid of that red color. If you don't believe me, I am mentioning here two implementations or two possible implementations of how read-write log can be implemented. This is like simple implementation. The real implementations are, let's say, a bit more efficient, but there is always in every operation read log, read unlog, write unlog, there is always an atomic instruction there. So perhaps the simplest implementation of read-write log is that you use one mutex. This mutex is used for access to protect access to this reader's active variable, and then you use semaphore, which is used by writer. So writer is very simple. If you want to write, you just wait for the semaphore. Once you get the semaphore, you can write to the data and then return the semaphore back. Readers, it's more difficult. Reader locks the mutex, increments the number of active readers, because the point here is to simply count how many active readers are there at any point in time. Hence, there must be this atomic operation. If we are the first reader, we just wait for the semaphore because there might be some ongoing write operation. If we know there is no ongoing write operation, we unlock the mutex and continue, and the read unlock operation just does the opposite. Logs the mutex, decreases the number of active readers, and if we were the last active reader, we pause the semaphore, meaning if there is a writer or updater waiting for us, we will just unblock it so that it can continue. So this is a very simple implementation in terms of lines of code. It has one problem: readers have priority over writers. So if you have situations like this, that you have multiple CPUs, all CPUs are just reading as you have with multiple writers, it can happen that the updater will never get to the update because there will always be some reader, and because here readers have priority, the updater will just wait indefinitely, not be able to updating. For that reason, you can have different implementation of read-write log. where writers have priority. You can see that this write operation is more complex. It uses log and it uses a conditional variable. Both this log or mutex and conditional variable, they both use some atomic instructions under the hood, and here you somehow track how many active readers are there, how many writers are waiting, and then use some conditions just to make it work. Why I am saying that, today you will get a homework where you will work with that, and if you don't select the proper implementation of read-write log, where writers have priority over readers, your example will not work. So you have to do something about that, and you know that you need to know about the fact that there are multiple implementations that behave differently. Otherwise, your program will not work. So we have read-write log. As I said, there is still quite a lot of red color. Ideally, we would like to have something like this. It's read mostly workload, so we have many readers. We don't want to block them at all. We just don't want any overhead, any atomic instruction. We just want to read very efficiently. And if we are updating from time to time, we just want to update it without blocking the readers and so on. In this example where we have just 4 CPUs, it's pretty like simple, but imagine this supercomputer where there is 4096 CPUs. All these 4095 CPUs are executing the read operations, and then just the single one is executing the update. So surely you don't want this updater to block all the readers, and at the same time you don't want those readers to use those atomic instructions at the beginning and at the end, because on this 4000 CPU system this would lead to performance disaster. So can we have this? Of course the answer is yes, and the question is how much it costs us, how much effort or whatever we need to invest into that. And the answer will be in the rest of the lecture. The technique, actually the technique has different names, but I will use the name which is used in the Linux kernel, and the name for this technique is called RCU, which stands for Read Copy Update. And as a teaser, the main advantage of using RCU is that it's a scalable synchronization mechanism for read mostly workload. So what does it mean, scalability? Scalability means that the more CPUs you put to your program, the higher performance you get. And as you can see, or we will see there are, or differently. RCU is a general mechanism, general principle, and there are multiple implementations of this mechanism. What you see, those lines here, those are different implementations of the mechanism. Some of them are very efficient. The more CPU you get, the higher performance you get. Some are less efficient. They have some other advantages, but it always holds that the more CPU you give to the program, the faster your program will be. If you look at this bottom line here, which is like 0, these are the data if you use mutex or if you use reader-writer log. Because it looks like it's 0, it would be unfair. So let's zoom into this 0. And if you zoom just to those bottom line there, you will see this. This is the performance of when you use mutex or read-write log for the same kind of program. And as you can see, the performance is really bad. So for mutex, Surprisingly, here the performance is slightly better for mutex than for read-write log. For nowadays, you can get slightly better performance for read-write log than for mutex, but still it looks something like this. The more CPUs you give to the problem, the slower the program actually is. So it's negatively scalable, and you definitely don't want that. So now we will look at how to implement such a nice scalable synchronization mechanism. I will show RCU on the simplest possible example, which is a single linked list. This is really this very simple example. If you are interested, you can find in the literature implementation of more complex data structures, including hash tables and so on. These are more complex, more tricky than we would have time at this lecture, so I am just using this very simple example, but this should be sufficient for you to get a basic idea what it is about. So imagine we have a single linked list containing 3 elements, A, B, and C. And we want to modify this B element here. What we do, first we perform the copy. That's the letter C, copy. We copied B to a temporary copy, which gives us that. Then we update this copy from B to D, so this will be the new value. So this is the letter U, update. Now there is no letter, but we will just replace the pointer pointing from A to not point to B, but to point to the new copy. It's pretty simple. And the last step is just waiting for all the readers to finish reading the list, and after we are sure that there is no such a reader, we can free the memory allocated to B. So this I think you are now saying it's trivial, there is no big deal about that. You are right, it's mostly trivial. I would say steps 1, 2, 3, 4 are trivial. Where the problems are and where the trick is this step number 5. Because step number 5 means that you have to wait for all the readers. And the tricky thing is that you don't want the readers to do some expensive tracking how many readers are there. If you do what, for example, this reader-writer log did, you calculate how many readers are there, it means that every reader needs to have an atomic instruction, this counter of readers, and if there is an atomic instruction, the more CPUs you have, the slower your program runs. So you don't want any atomic instruction. And this makes it especially tricky. So one way of looking at RCU is written here, that RCU can be seen as a mechanism which converts a scalability problem into a garbage collection problem. And let's see how it works. Before I will start explaining how things work, let's see some general idea. Yeah, I have already said that we don't want any explicit and expensive tracking of each reader, because this would be expensive. So RCU is based on somehow indirect way of determining the end of read-side sections, basically where the last reader which starts reading here finishes there. So at this point in time, we can finally free the old data, because now every reader sees the new data. There are different ways how to implement this indirect way of determining. Interestingly, some ways have even zero overhead. So that's very nice. There is really no overhead on reader side. The disadvantage is that you need to have certain structure of your application. If you don't want to modify your application to have that structure, there are other implementations which do not have zero overhead, but still have some reasonable overhead. There are still no atomic instructions at the reader side. Yeah, so there are RCU is basically composed from several mechanisms. Those mechanisms are implemented in certain functions. The functions here are the functions as they are used in the Linux kernel, or also in this user space library that you will work with exercises. So those initial steps of this algorithm, those are pretty simple. There are special operations like assign pointer and the reference pointer. Those are pretty easy. Typically those are just implemented with some barrier or even without barrier. And the tricky part is this synchronization, waiting for all the readers finish, which is typically implemented with a function called synchronize RCU. And before we go to talking about the actual implementation and seeing how it works, one note or question: does it make sense to use RCU in Java? Because we have little time, I will answer myself no, because in Java, you know, Java has a garbage collector, but so you don't need RCU to wait for this garbage collection. The thing is that the Java garbage collector has much overhead than what RCU offers. So if you have a language without garbage collector, you can have RCU, or the RCU can be more efficient than if you have the same thing in Java which has garbage collector, because the garbage collector has itself some overhead. It uses a lot of atomic instructions and so on. Yeah, so when you read some text about the RCU, there is quite complex terminology. So I think I am not going to explain everything. I will explain just a few things. The most important thing is the term quiescent state, and the term quiescent state is the time between read side critical section. So read side critical section is, like in case of mutex, between lock and unlock. Here we are not talking about mutexes, so read side critical section is the area between RCU read lock and RCU read unlock, and whatever is outside of that is called quiescent state. And the second most important term is the term grace period. And the grace period is a time after an updater updates data until it is safe to free the old copy of updated data. So this is called grace period. And basically the tricky part of RCU is to figure out how long this grace period is, so that I can I can free the data. How to use RCU? I think I will continue or show that at exercises. So I will just skip that. And now I would like to look at an implementation of RCU, which is one of the implementations. As I said, if you read about RCU, what you probably find is how does Linux kernel implement RCU. But here we are talking about something different, how this can be implemented in application which is running outside of the kernel. And here I will present what's called QSBR implementation, quiescent state, and I forget what BR stands for, quiescent state based reclamation. So here is how it works. There are multiple threads which can either read or write, and those threads, each thread has a counter which is per thread counter. The thing is that this per thread counter is only updated by a single thread. There is never a need for this counter to be updated by multiple threads. This means that you don't have to synchronize when updating this thread. You can just update this counter without any mutex and whatever. And then there is a global counter which is shared between all the threads and which is called RCU grace period counter. And maybe I will just, yeah. This is how updater updates the code. So for the simplicity, because this is read mostly workload, the updates happens infrequently. So for updates you can use mutexes. It's infrequent, so there is atomic instruction and it's not a problem. So you do this copy, you update the data, you assign the new pointer, and then you call synchronize RCU, which just waits for the end of the grace period, and only then you can free the data. So imagine that you call RCU, synchronize RCU here, and what it does. It increments this grace period counter to value here number 3, and basically then it waits until all other threads go through the quiescent state, and all other threads in quiescent state are forced or should implement call to RCU quiescent state function. And this RCU quiescent state function is pretty simple. It just reads this shared variable and stores the value to this local counter. And this synchronized RCU just goes from time to time looking at those variables, and after it sees there are all 3 values in it, all 3, it means that all readers went through the quiescent state, which means that all readers finished the reading of the list, and the data can be freed. It looks like pretty simple, pretty dumb, but if you think it's simple and dumb, you missed a lot of points. So there is some kind of implementation. The implementation of that fits into 2 slides, so unfortunately we don't have time to go through that. But I suggest you to read this. It's not difficult. It's pretty simple. I think that if you don't understand these two slides of the code, especially this synchronized RCU, which is the tricky part, which is like just this half slide, you don't understand how RCU works and what's the principle. And the conclusion here is, or the conclusion, like what I want to say, that if you want to get good grade like A or B from this course, I basically want you to understand what happens here. So read that. In the afternoon you will have homework where you will use that, so you will have a chance to like understand what's going on and how it is used. And yeah, if you do it correctly, you will be lucky. You will get that nice performance. The more CPUs you have, the faster you will be. Yeah, so then there is another implementation. I have to skip that implementation, and I will just conclude that RCU is very nice synchronization mechanism for a RISC mostly workload. If you want to have scalable applications with that workload, this is probably the only way how to achieve the scalability, so you should definitely understand how it works and use it if you need it. Thank you.